Hello differential equation students, here's the final lesson of the course. Lesson 15, Systems of Linear ODEs 2. This topic corresponds to the chapter 9 of our textbook, the latter half of chapter 9 that is. This notebook consists of 7 sections, among which we have 3 optional sections toward the end, sections 5, 6, and 7, and these are highly theoretical, and also first 2 sections are reviews. Reviews mostly on lesson 14, but some of them refer all the way back to lesson 13. Now that leaves only 2 sections here, sections 3 and 4. How much of them will be required and how much of them will be diverted to optional topics, I'm not so sure at this moment. I'm going to make an appropriate decision as the semester progresses. For now, let's just cover it as planned. And here we go. Let's begin with a review. And this is a review, so let's go as quickly as possible here. Here is the definition of the matrix exponential, and this is valid for any square matrix. And please note that this corresponds precisely to the real exponential, the Taylor-Maclaurin series expansion here. So this is just a natural extension of previously known case. Also, if I replace this matrix A by A times T, and T is a variable and A is a constant coefficient, in that case, basically, I'm replacing all these A's in the first expression here by A times T, and that's going to give me the second expression down here. And that expression, the second expression, is particularly useful for systems of linear ODEs with constant coefficients. This coefficient matrix A is constant, then you're going to be using this one. Now, what if we have variable coefficient? The coefficient matrix A already has some non-trivial expressions of t. Then we can't do this down here. We are stuck here. And this is going to be a little bit harder as a matter of fact. And that situation will be covered at least to a certain degree in section 4 of this notebook. But that can wait. In any case, in lesson 14, we did only this part because in lesson 14, we did nothing more than systems of linear ODEs with constant coefficients there. Okay, that was matrix exponential. And here is the simplest case of the matrix exponential. When the matrix is a diagonal matrix, we take the exponential of the diagonal entries. Same for we have d times t, because times t will not change anything here in the top or bottom because 0 times t will be just 0. So we have times t only on principal diagonal. So by the same rule here, the exponential will be just e to the lambda t down there. The proof is here, but it's tedious, but they're elementary, so I'm going to leave the details to the students. And we'll just move on. Even simpler case, when the diagonal matrix is a 0 matrix, then we have all zeros in the diagonal. So we have e to the 0 power, which is 1 in the principal diagonal, otherwise all 0. So what do we have? We have the identity matrix. So e to the 0 power is equal to the identity matrix. And this extends our real arithmetic rule. E to the 0 power equals to 1. Okay, next topic is the matrix exponential rules, and this one we already discussed. Here's a second rule. If A and B commute, A times B is equal to B times A, then we can use this exponent rule. E to the A plus B power is equal to E to the A power times E to the B power. Now, if they do not commute, that's going to be a problem as a matter of fact. You see, look at the left-hand side here. A plus B. That's always commutative because this is addition. Now look at the right-hand side. That's multiplication, so that may not be commutative. So left-hand side we can switch A and B. Right-hand side, we can't. That does not make any sense. So this rule cannot possibly be right if A and B do not commute. If A and B commute, then yes, it'll turn out yes. Now, a special case when B is negative A, in that case, we can easily see that A and B or A and negative A commute. A times negative A is equals to negative A times A. That's easy to calculate because what do you mean by negative A? It is negative 1 times A, and negative 1 is a scalar, so I can always pull it out. So they commute. So we can use this rule here. And consequently, we can do this computation and that computation. And therefore, what do we have? E to the A power is always invertible, and the inverse is e to the negative A power, and vice versa. Let's go back here. A may or may not be invertible, but e to the A power, that's always invertible, and the inverse is e to the negative A power. Alright, so much for matrix exponential rules. And let's do some calculus with matrix exponential. And this first rule is very, very important. Oh, by the way, one more thing. These two commute. So exponential times A is equal to A times exponential. They commute, so you don't really have to worry too much about where to multiply A. You see? Take the derivative of this exponential. Exponential always stays the same, so we have that. Alright, so far so good. But then again, by chain rule, we have to multiply the derivative of the inside. Look at the derivative of the inside here. We have A times t, so that derivative should be A. But do I multiply it here on the left-hand side or on the right-hand side? Where do I multiply? Luckily, we don't have to worry about it because they commute. Why? Well, let's go back to this definition here. This is e to the A power, see? And then what is A times e to the A power? This. And is that the same as e to the A power times A? Please check. It's not going to be too difficult to check. It's going to be true. The detail is left to the students. So you don't really have to worry about where to multiply A. The chain rule goes everywhere anyway. So we can apply this rule, and one of more important application is right down here. If you have a homogeneous system of first order linear ODE with constant coefficient like this, and an initial condition, then the solution follows from this formula here. So if you calculate e to the AT power, then multiply by y star, which is explicitly given, along with the initial condition, or you can just put C1, C2, C3 all the way up to Cn if you're looking for just general solution. In any case, the key is this part. If you calculate e to the AT power, then finding out the solution of the homogeneous system is easy. As for the second formula here for integral, I don't see any use of this. I don't know. It may be useful, I don't know. This is really useful. This one, well, I just listed it because this is a counterpart of the derivative rule, and this one is for integral. But this one is far more important, and we have a nice use here. Now, how did he actually use this formula here? Do you recall these problems from, let's see, lessons, I think they appeared lesson 13a and also lesson 14, both. Well, both times I used this one as a benchmark problem, so why don't I do it this way this time? So this thing is y prime times yb. So this one is y prime times b times y. Y of 0 is y star, this form. Oops, excuse me. Y star is, of course, this matrix here, And then let's name this one as matrix B because I'm using the same character down here. So by the same formula that we just discussed, this is a formula. And then if we calculate this matrix exponential, and if we get this, then the rest is an easy computation. Get the matrix exponential and multiply by y star, and there you go. So the key part is to calculate this matrix exponential, e to the bt power or e to the at power. And how do we do that? And this is one of the more effective way to do that. Previously in that example, I don't know whether everybody remembers that or not. I hope that you do. And we just relied upon log, calculating bt, b squared, t squared, b cubed, t cubed, b to the fourth power, t to the fourth power, and so on. And hopefully we can find out a pattern and go from there. And then write down the Taylor series and then find out pattern from there for each entry. And if stars line up correctly and I find out appropriate pattern for all those, then we have an answer. But then again, oh come on, normally people are not that lucky. So we need better tool, and this is one of those better tool. We can actually calculate the matrix exponential using the Laplace transform. And by the way, this formula here corresponds precisely to the real function case, like this. If you're unsure, you can always go back to the Laplace table in page 123 of our textbook. You can see both of those there. And this expression corresponds precisely to this one, because here for a real function we have reciprocal, and the corresponding quantity for a matrix is inverse matrix. Basically they are divisions. And then as for exponential, e to the at power, e to the at power, clearly they correspond. So this formula here are extension of these formulae as a matter of fact. Now, how do we work this one out? For simple matrix A, we could actually work out. And here are some example problems. For example, what about this matrix here? Let's go back to that formula here. We're going to be using this formula, right? Alright, that's how you get e to the at power. So in order to find it out, we need to get this one, Si minus A inverse, which we call the resolvent matrix. And calculate Si minus A, and then take this inverse. And this is just 2 by 2 matrix, so inverse computation is not difficult at all. We use this A, B, C, D, and its inverse is 1 over AD minus B, C, the determinant, and then switch the principal diagonal, AD becomes DA, and then take negative of the others. And there goes the inverse formula for 2 by 2 matrix. Of course, if this becomes 0, then the matrix is not invertible. That's basically what I did here, and that's how I got this denominator here. They're coming from this determinant out here. Now that we have this expression, we can take the Laplace inversion. Take the decomposition by partial fraction, and that of course is a heavy-duty calculation, so it's going to be better if you use computer algebra system like this. And once the decomposition by partial fraction is done, then you can always go back to that Laplace table in page 123 of our textbook, and we get this, and that's the answer, and you can stop there. But if you want to go just one more step, please note that we have e to the t power and e to the negative t power. And they're all coming from the denominator here, s squared minus 1, and it has two zeros, plus and minus 1. So based upon that, we have e to the t power, and then we have the coefficient matrix, e to the negative t power, and coefficient matrix like that. We can decompose this big matrix expression into this form with the e to the t power, where we have the eigenvalue of 1 times coefficient matrix and e to the negative t power times the coefficient matrix. And this thing, the student who has some strong background in linear algebra will recall it as the eigenvector. That too is the eigenvector. And the eigenvalue corresponding to 1 here, and the eigenvalue corresponding to the negative 1 here. Okay, if you didn't understand those terms, that's fine. So, that was an effective way to calculate e to the at power. This formula, calculate the resolvent matrix and take the Laplace inversion. Now, taking the inverse matrix was easy for a 2 by 2 matrix. For 3 by 3 or higher, taking the inverse is already a pain in the rear end. And once you do that, you have to take the Laplace inversion, which means you have to take that decomposition by partial fraction for each entry. And say, for example, if you have something like 5 by 5 matrix, then you have 25 entries, and you're talking about partial fraction 25 times, for God's sake. Theoretically possible, but practically that's impossible. At least for human, it's impossible. Computers can handle it, of course, because everything is completely algorithmic, but still, maybe not the best way to do. For 2 by 2 it works, but for higher it doesn't work very well. And that is one of the motivations for section 3, Fulmer's method. We look at an alternative way to find that e to the at power. And if you have 2 by 2 matrix, then this is not really useful because the conventional method I just talked about is usually better. But 3 by 3 or higher, in that case, you're going to appreciate this method here. Okay, that's where I'm going to stop. And we're going to discuss section 2 of this notebook in a separate video.